Welcome to LabMinutes.com. In this video, we will look at more advanced features of the EZVPN. We will start off with a feature called Network Extension and Network Extension Plus mode. And what it does is, with the client mode, everything behind the client device is NATed to the IPs allocated by the head end. So the access is only one direction. So basically, if you have a server located in VLAN 128 in this diagram, for example, which is behind the client hardware, a device in VLAN 32 would not be able to access that because everything is behind a NAT. So what Network Extension and Network Extension Plus does, it opens up the whole subnet that you define on the client, on the hardware client side, to be visible to the head end side. So the access can be bidirectional. Okay, then we're going to look at multiple subnet support. So far we only deal with a single subnet, which is VLAN 128. If you have or happens to have multiple VLANs or subnet behind the hardware client that you need to allow access, then we will look at how to do exactly that. And we will, at the end of the video, we will look at the interaction with network address translation and see how that works with EZVPN. Okay, so our lab setup here is just an extension from our previous lab with the router as a head end. So from the previous lab, we have two subnet, VLAN 32, VLAN 128, and we have the hardware client enable or running on the client mode. And we had the connectivity established between the two subnets. So we're going to make a slight modification by adding the VLAN 129 into the lab here. So that's going to be our starting point. If you want to see a more elaborate configuration on the lab setup and how we get to this point, please review our previous video, which is SEC0019, EZVPN with pre-short key and XAuth with the head end router. Okay, so now we're just going to continue with what we have right now, but to see where we are, the tunnel is already up and we have a phase 1, phase 2 established with the ping going already. So we have a successful ping from the machine on 128.32 pinging at 32.1. There we do show crypto IPsec client EZVPN. Here's all the attributes that was downloaded with the split tunnel subnet. But if you run a debug IP SMP on the switch, you see the IPs the switch is seeing the IP is coming from is 100.32, which is the IP allocated from the pool to the hardware client. So the first features we're going to look at is the network extension mode. So if you go to R2, and this is purely a client configuration, so there's nothing you need to do on the head end side except from the routing that will make a change in a second. So if you do show run client EZVPN, okay. Scroll up under here. Right now is mode client, so we're gonna change that to, let's see, mode network extension. Okay, so as you do that, the tunnel resets, and I'm not sure if you remember from the log messages from when you run the client mode, that's actually an extra log message that tells you that the NVI interface, which is the NAT virtual interface, will be up as well. But since we are doing network extension, there's no IP being allocated from the head end, so we no longer see a 100.32 IP or 100.x IP anymore. Okay, so now that we are in network extension, you can see we lost our ping, so something must have changed. If you go to R1, show crypto IPsec SA, so you can see immediate difference right here. Before it was all 0 to 100.32, and now it's become a 32.0 to 128.0. So now the actual VLAN 128 subnet is visible to the head-end side. Okay, so if you do show IP route static, and you see because we have a reverse route injection turned on, it installs 172.16.128/24 subnet into the routing table pointed out as a static route pointed out the outside interface. Actually, it's a recursive pointing to the remote, the client IPs, which eventually will point out the outside interface. So if you check now on the switch 1 route static, previously we have a static route of the 100.0/24 pointing to the router R1. Since that's no longer true, we need to let the switch 1 know the presence of the subnet. So there's a couple ways to do that. You can just, as simple as installing a default route, not default, the static route 172.16.128 and just point it to the R1 as well. But we're just going to prep this for our second part of this lab with the multiple subnets. We're going to go ahead and do the dynamic routing protocol with EHGRP. So on the switch 1, we already have EHGRP turned on fast 01. Now we just have to turn on EHGRP on R1 and then redistribute the static. So any reverse route or static route that's being installed by the reverse route injection can be redistributed into EHGRP and then eventually reach the switch 1. So we're going to do prefixless just to include the subnet that we expect in this lab, which is the 2 VLAN 128.129 on the client side, as well as the IP pool subnet that will be allocated, or that has been allocated to the client, which is the 16.100. Then we're going to go route map static to EHGRP. This is for redistribution. Permit 10 match IP address prefixless. Then call site. Just going to go and set metrics as the get into the habit of doing that. Okay. Then other route EHGRP1, no auto. Let's see if that's something configured already on. Okay, looks like we don't have anything yet, so there will be no auto, passive default, no passive, fast 00, which is the inside interface of the R1. And then we go network 172.16.2.1, actually 2.2. Okay, see our neighbor immediately comes up. Now we're going to get into redistribution from static route map, and we call that static to EHGRP. Okay, you can do show IP prefix list detail, and you can see that the ping came back on the background. If you look at here, there's a hit count of 1, so that tells you that 172.16.128 has been redistributed into EHGRP. So if you do show IP route EHGRP on switch 1, you can see it right there, it came across. So now switch 1 knows how to get back to the remote VLAN 128. We have a complete network IP connectivity. That's why we have our ping successful. And just to show you, if you from the switch 1 we have, before we can only ping from the VLAN 128 to VLAN 32, but now that we have bidirectional reachability, we can actually initiate a ping from switch 1 to R2 interface, which is 128.1. So let's see, 128.1 source, don't forget to source, VLAN 32. Okay, so now if you have a server or a device that needs to be accessed from your head end, then you can do so. All right, so there's also another mode called Network Extension Plus. So let's turn that on, and then we'll point out what's the difference with that. So let me go and find the command to get under the client EZVPN. If you go mode, and you can go Network Plus, okay. Again, it's going to bounce the tunnel. Let's give it a second. Okay, to show IP interface brief. You can see one main difference is the IP that was allocated to loopback 10,000. So in addition to having a bidirectional access on the subnets on both sides, so it's basically a combine of the client mode. If you think about it, it's the combine of client mode and the network extension mode. So you have the benefit of the bidirectional access, as well as you get an IP that's been allocated from the head end, and you can use that for troubleshooting purposes or something else. But from what I've seen, it's not really much use unless there's a need for it. You can just run network extension. So from the switch one, just to show you, we show IP route EHGRP. Now that we have EHGRP running, it also learns the 100.33, which is the IP that's allocated to R2. And if you're trying to ping 100.33, you can see you can ping that. So that's what's different between the network extension and network extension plus. Okay, so let's change this back to just network extension. Next, we're going to take a look at a multiple subnet support on the client side scenario. Okay, now that we're back on network extension. Yep. And the way to do that is by access list. So we're first going to come up with an access list, because by default the hardware client is only going to include the directly connected subnet or the subnet on the interface that you enable EZVPN Insight on, which is alfast 00. Okay, so EZVPN Insight, so those are subnets that's going to be included in the IPsec. But if you want to include additional subnets, especially if it's multiple hops away and not directly connected to the hardware client device, in this case for us is VLAN 129, which is an extra hop away behind. We have a layer 3 switch in the middle, so it's not directly connected. And the way to do that is through access lists. We're going to call it local net. So I misspelled access, there we go. And then you go permit IP 16.128.0 any. And in addition to that, 129.0 any. Okay, and then you define that under crypto IPsec client EZVPN and here's an option for ACL. So let's say it's here, specify access list identifier for SA, or Security Association Establishment. So ACL, you do local net. Okay, so let it bounce. And if we just show crypto IPsec SA, again, as long as we have the ping reachability in the background here, we know the tunnel has been established successfully. So if you look at the phase 2, we have a 128.0 and 32.0 SA. And then, let's do this, might be easier. Include ident. There you go. So you got 128.0 to 32.0 and then 129.0 and 32.0. Okay, so just by associating your client-side configuration to access list, you can pretty much associate as many subnet as you like on the client side to be included on the tunnel. And whatever that's included on the tunnel, it will get installed as a static routes by the reverse route injection on the head-end side. So because we have the dynamic routing set up, switch 1 immediately picks up the additional subnet that we just added, which is 129. And that's why, let's see, we can try to ping from 129 because our ping here is coming from 128.32. So here we just, in our lab here we just have one switch, but we put the switch in different VRF. So on the client side, it's a VRF site, and we can ping, try to ping 172. Actually, let's try this. We can ping 172.16.129.1. Source interface VLAN 32. You can see we can ping successfully. So switch 1, VLAN 32 now has access to both VLAN 128 and 129. Okay. And just to show you also, the access list that you define doesn't really have to match the actual subnet VLAN. So if you have, for example, 10 subnets of /24, you don't really need to do like 10 lines of those. You can actually summarize them. So basically whatever you define the access list, the router would take that and include that on the security association. So let's delete or modify our access list. So no IP access list, extended local net, and put that back with the permit IP. And we have like 2 contiguous subnets of 128, 129. So we're gonna summarize to a /23. I guess we have 2 /24, then any. There go do clear crypto IPsec client easy. Okay. Let's wait for it to come back up. Looks like it's already up. So you can see here the directly connected subnet on the hardware client is always going to be there, which is 128.0/24 right here, rather. But the subnet that you define in the access list is also included right here, 128.0/23. Okay, and again, coming back to the switch 1, then the switch 1 will see both subnets. Okay. And the ping still works. Alright. So that's the multiple subnet support. Next we're going to look at the interaction of the EZVPN and the network address translation. The first thing we need to do on the router R1 side, we need to define which subnet you want to allow NAT enable. So we're going to call EZVPN NAT for the access list. And then permit IP. We are going to do the whole subnet of the site, which is 128.0/23 to any. And then under crypto IPsec client EZVPN, there's an option for NAT. So NAT ACL, then you specify what the ACL that we just created, which is EZVPN NAT. Okay, bounce it, and then you go NAT allow. So do show run EZVPN. So here's our NAT commands. Right. Next, we're going to go ahead and create a conventional NAT configuration. So here, we're first going to start off with pat. So assuming a host needs to be able to access internet, we're just going to use the 2.2.2.1 on the internet switch here as our test ping. So if we do that right now with a ping site 2221 source from VLAN 129, we're not getting anything. And if you actually run debug IP ICMP, let's stop the ping in the background here so it's less noisy. Okay, you can see the IP is coming across and hit the internet switch is the native IP, which is 129.1. So we're going to go ahead and configure a NAT for that. So in R2 IP access list, NAT ACL, go deny IP. So we don't want anything from the site to the private IP, let's say 0.15.255.255 to match our NAT. And then any. Okay, so just internet traffic. And then you go IT NAT pool. NAT pool. We're going to pick 222.11. Prefix. .24. Okay. Then IP NAT inside source list. NAT, call it NAT ACL, right? Yes. NAT ACL with the pool of NAT pool, and we're going to do overload, which is pat. And last, we're going to have to define what's the inside and outside interface for the NAT. So fast01 is our NAT outside, and fast00 will be our NAT inside. Okay, now that's back. IP NAT inside. Okay, so let's go ahead and try that again on the switch one with a ping. Okay, the ping went through. See right here, and then we see our debugs messages with the ICMP echo coming from echo request coming from 222.11, which is our padded IP. We show IP NAT translation, and we have an entry that reflects that on the NAT table as well. Okay, so that's the NAT for going out to the internet. What about the NAT going over the EZVPN? So let's say you run into an issue with the overlapping subnet. It turns out that there's a IP conflict on each side, so you need to NAT an IP on one side to resolve that conflict. So let's assume that we're going to do a static NAT of the IP 172.16.129.1. So we're going to do 172.16.129.1 and then have a static NAT going to 172.16.128.100 when it goes to the 172.16.32. Okay, so now actually we're going to do the static NAT for the traffic that goes over the tunnel as well as the traffic that goes to the internet. So we're going to see if we can have a server that can be accessed over the tunnel from VLAN 32 as well as being accessed from the internet. Okay, so we're going to configure static NAT. So IP NAT inside source static 172.16.129.1, and then we want to map that to 172.16.128.1 100. Okay, so now if you go back to switch 1 and try out pings again, 172.16.32.1, you can see our static NAT is working because the VLAN 32 is seeing the ICMP echo request is coming from 128.100, which is our NATed IP here. Okay, and you can see one is sent and one is received. Since we're using the same switch, you can see here that switch 1 on the left and switch 1 on the right is the exact same switch. That's why we're seeing both send and receive. So when it's receiving, the NAT is already undone. That's why it's coming as a destination 129.1. Okay, so that's for the NAT going across the tunnel. At the same time, you can do a NAT going to internet. So, of course, not from the same. You cannot have those up concurrently though, because unless you do things like policy NAT, because this router doesn't really know what scenario to use which NAT. So, without doing a policy NAT, you can have one of those entry at a time. So 222.100. Just to show you the static NAT going to outside also work. So now we're back on switch 1. If you ping that again, our NAT is gone. Let's see. So you can see right here when you're trying to ping, now with that static NAT, you're trying to ping 32.1, it's coming across as 222.100. So it has no idea if the traffic is actually going at the tunnel, and it should not be NATed. And it should be NATed only when it goes to internet. So unless you come up with an access list to define the policy. But if we instead ping the internet, that works perfectly. Okay. So I come across as 222.100, and just to show you, we can test from the outside. So you can telnet to 222.100. But we need to define VRF from internet. So VRF INET. Right here, we are originating a telnet session to the switch 1 that's NATed to 222.100. And here I can see, since we don't have password set, but we know we were able to open a telnet session, so our NAT also works. If you do show IP NAT translation, okay, that's the telnet session that we just did. So 222.100 gets NATed to 172.16.129.1. Okay, and that's the ping that we did as well from inside to the outside the internet. Okay, so the NAT is continued to be supported in the network extension plus, not so much with the client mode, because client mode by default the traffic gets NATed to a single IP already. But with the network extension plus, the NAT indirection occurs as normal. Okay, so that wraps up our video on additional features on EZVPN. Thank you for watching LabMinutes.com. I'll see you guys in the next video.